actually talking about work that I've done with Mark and Gustavo about Yukawa interactions in quantum gravity. And I'm actually very excited to talk about this. I think we have very excited about the results that we have obtained in this collaboration that actually started 2 years ago in Sardinia. And since then, we have come a long way, understood a lot of things. And I think, yeah, we've come to a nice overall thing in the end. So the topic is Yukawa interactions, and the plan of the talk is that I first give you a slight overview of why I think this is a very important topic that needed to be addressed. So why do we actually need to understand very well how gravitational fluctuations influence Yukawa interactions? I will shortly present you what has been known before our work and what are the implications of our work, and then I will come to our results and how we have obtained them. The main point that we would like to understand is how and if the standard model can actually emerge from an asymptotically safe fixed point. So what I'm showing you here on the slide is the running of the marginal standard model couplings as a function of the RG scale. And in the IR, they take their known values as measured at the LHC. And then you can evolve them to the Planck scale and beyond. And most of the time, they remain very well perturbative. And only very, very far in the UV, you run into a Landau pole, which determines the effective end of the standard model. Namely, in this case, the U1 hypercharge coupling runs into a Landau pole around 10 to the 40 GeV. But aside from the U1, also the Yukawa coupling would run into a Landau pole, and the quartic scalar coupling would run into a Landau pole. Only the non-abelian gauge couplings are naturally asymptotically free on their own. And of course, this is the story without quantum gravity, and we expect quantum gravity fluctuations to maybe set in around 10 to the 19 GeV. And then the question is, how will these quantum gravity fluctuations change the running of the marginal couplings? And can then the standard model, or maybe the standard model with possible extensions, run into an asymptotically safe / free fixed point? And for this, we need to understand what is the interplay of gravity and matter. And the system that I'm talking about you today is the gravity Yukawa system. And yeah, let me just use this slide here to give you a short definition of what I mean with that. So we are interested in studying this Baire action, which includes the Einstein-Hilbert action with the cosmological constant and the Ricci scalar and the Newton coupling. And this is now coupled to a minimal matter action, which has NS scalar fields with a standard kinetic term, NF fermions. We also take NV gauge fields into account. And then it has this important term here, which is the last one, namely the Yukawa interaction, which we would like to study. As a short remark, I should say that in our computation, it's not really relevant for what I will be saying, but in our computation, we have only one scalar field which couples through a Yukawa interaction, while all the fermions participate. It's a minor detail and actually won't matter in the end too much. But now in this minimal setup, which is kind of a toy model of the standard model, you can now go ahead and you can compute what is the gravitational influence on this running Yukawa coupling that I have defined here. And if you want to do so, you would sit down, you would write down the diagrams that I've given here in the last line, compute those. Here I'm only selecting the gravitational diagrams. There's the other diagrams, which are the pure matter diagrams. You would compute those and see what is the beta function of this Yukawa coupling. To understand better what is going on, I would like to first give this in a schematic view. So in terms of a schematic beta function, these schematics go back to Astrid and Aaron. And schematically, you can write down the Yukawa beta function in its standard matter part, which I write down here. So the Cy is some coefficient that depends on what kind of matter system you actually look at, number of fields, etc. And this is a positive coefficient for the system. And then, so the pure matter part and then you have the quantum gravity part. And here I'm writing this down where I separate out the Yukawa coupling and the dimensionless version of the Newton coupling. So just to go back for a second, all these diagrams here, they're linear in the Newton coupling. There's one quantum gravity propagator, and then you have always one Yukawa coupling in each diagram. So all of these diagrams are linear in the Newton coupling and linear in the Yukawa coupling. So it makes total sense to write it down like this. Minus sign is separated out for convenience. And then this factor Fy is some number that might depend on other couplings, such as the cosmological constant. But for now, you can think of it just as a number. And what you can see immediately, the pure matter part wants to drive the coupling to larger values. This is the reason why the Yukawa coupling by itself would run into a Landau pole. And then we have this gravitational part, of which we at first we don't know the sign, but since I have conveniently taken out the minus sign and assuming now that Fy is positive, you can actually balance out this Yukawa interactions with the gravitational fluctuation, and you can find an asymptotically safe fixed point, and you can avoid the Landau pole. And this is precisely what is shown in this little cartoon flow here. So if you are exactly balancing out the Yukawa coupling and the gravitational fluctuations, you can have the asymptotically safe fixed point, and you have the trajectory which would be leading here downwards. Here, if you have a larger Yukawa coupling, you would nonetheless run into a Landau pole, and if the Yukawa coupling is smaller, then you would run to an asymptotically free fixed point. So from this little cartoon, you can already see you want Fy to be positive, and if Fy is positive, then you will have an asymptotically safe and an asymptotically free fixed point. The crucial quantity is actually not Fy. The crucial quantity here is the critical exponent of the Yukawa coupling, which I'm writing down here, which is the negative derivative of the beta function. And so it's Fy evaluated at the fixed point of the Newton coupling. And if Fy is positive, this is now positive, which means the Yukawa coupling is relevant at its Gaussian fixed point and irrelevant at its interacting fixed point. Because it's irrelevant, you would get a predictive power from this interacting fixed point. And of course, there have been many computations of this coefficient Fy at leading order. I'm listing some, not all here. But before I dive a little bit deeper into this computation at leading order, let me also, so this is still in the toy model where I only have the Yukawa gravity system. Let me also shortly highlight how this would look at the full standard model system. So if we take the standard model, we of course also have gauge interactions and the quartic. And if we are choosing that, or not choosing, but if we want to use the Gaussian matter fixed point to find the standard model infrared, we need that Fg and Fy is larger than 0. Then also the hypercharge coupling goes to its Gaussian fixed point in the UV. You might think you also need F lambda larger 0, but as it turns out, you might not necessarily need that. Instead, if F lambda is negative, this leads to a prediction of the Higgs mass approximately. So this is just an example of how the standard model in infrared can actually be UV completed given Fg is positive, Fy is positive, and maybe F lambda negative. There's also other solutions how the standard model can emerge at low energies from the UV. And I'm taking here the recent example of Astrid, Zeus, and Aaron, where they use an interacting fixed point, here interacting in the bottom Yukawa coupling to reach the standard model in infrared. The thing that I want to highlight here most is now that Fy is slightly negative. So this condition that we want to have Fy positive actually can be slightly softened. So you might be getting away with a small negative Fy, but for the rest of the talk, this actually won't matter much, because if it's small and negative or 0 and positive is numerically speaking not a big difference and actually indistinguishable, I would say, in our computation. But a small negative value is actually feasible. So if these gravitational fluctuations have a nice behavior towards the running of meta couplings, then we can actually find the standard model emerging at small energies from the asymptotically safe fixed point. How do they actually look, these how does this contribution to the Yukawa coupling actually look at leading order? And as I said before, there have been many leading order computations before us. Here I'm just showing you what is the leading order result for our computations, also because these are scheme-dependent numbers. And in our computations and in other computations, these critical exponents turn out to be negative. So here I'm showing you two results, which is minimal matter. So I only have one scalar field and one fermion and no gauge bosons. And here on the right, we have standard model matter content. And in both cases, the critical exponent is negative, which is the wrong sign, which means the Gaussian fixed point at leading order is irrelevant. And Yukawa couplings would be identically vanishing in infrared. So if this would actually hold beyond leading order, this would actually imply a no-go theorem for fundamental Yukawa interactions in asymptotic safety. I'm not saying Yukawa interactions, I'm saying fundamental Yukawa interactions, because of course they could be in principle generated in some other way below the Planck scale effectively. So effective Yukawa couplings not generated. That's a small difference. Here in the middle, I'm also showing you then how these critical exponents at leading order depend on the gravitational fixed point values. So here red means that theta y is negative, vanishing Yukawa interactions in infrared, and green means theta y is positive. Then you can generate finite Yukawa interactions in infrared. And as you can see, the fixed point values for minimal matter and for standard model matter are far away from any region where you can actually generate finite Yukawa couplings infrared. So from the leading order perspective, this is actually a pretty negative statement, but not all hope is lost. First of all, let me emphasize that even at leading order, these quantities actually, this critical exponent has actually a rather strong scheme dependence. So here I'm showing you two examples of what people looked at before. And the first one is a regulator dependence. Here we varied one parameter, one regulator parameter called gamma mg. And this quantity that I'm showing here is basically negative. So this is actually the negative version of the critical exponent or of Fy equivalently. So here negative is relevant and positive is irrelevant. So for the standard parameter of the regulator 1, you have the result that theta y is negative, but by a mild variation, changing the regulator parameter from 1 to 2.6, you can actually find that this critical exponent becomes positive. Or here's another example. If you include higher order curvature operators, or in other words, you introduce new propagator poles, then you can also find a sign change in this critical exponent. So here the green dashed line is the result for r min u equals 0. And then here down here you have a positive critical exponent. This is what Astrid and Aaron found some time back. So at leading order, results point, naively speaking, towards an irrelevant Yukawa coupling, but there's already then people observed some inherent scheme dependence. So for us, this was clearly the statement we should look at this beyond leading order, because clearly the results at leading order are inconclusive, or at best inconclusive, at worst have a negative result. So let's go beyond leading order. This is what we did in our work. And the first thing that I want to emphasize here is that the critical exponent is now not given anymore by the negative derivative of the beta function. It's the negative eigenvalues of the stability matrix. And this is, of course, the general definition. But I also want to emphasize that the critical exponent is, of course, scheme independent. while this quantity that I talked about in the previous slide is not. So in the previous slides, I basically talked about this quantity Fy G star, which at leading order is identical to the critical exponent, but beyond leading order, those quantities are not identical anymore. And this theta y is a scheme-independent critical exponent, while on the right-hand side, only the sum of all terms inherits this scheme independence. So it's natural that studies at leading order find a scheme-dependent result of Fyg star. And yeah, so in our work, we wanted to charge this territory and derive beyond leading order terms in this critical exponent. Actually, you should have complained to me because I'm already using words like leading order, beyond leading order. What do I actually mean by that? So before I talk about this, I should actually define what is my expansion scheme, what is leading order, what is the next to leading order expansion. So there's actually several options, and the options that I'm presenting here are actually, in some sense, even a historically accurate way how we went through the system. Namely, at first you could think I'm just doing an expansion in the mass dimension of the operator. So at leading order, I include all marginal operators. Then I include all dimension 6 operators. Then I include all dimension 8 operators. And I'm obviously selecting the ones that contribute to the Yukawa coupling. And this would be a valid expansion scheme. But through the course of our work, we realized actually this is not the best. Mainly because if you cut operators at mass dimension 6, this does not even include the full two-loop result that you would get in a perturbative computation. It seems that the system behaves actually better under this option 2, where you say that the expansion is not in the mass dimension of the operator, but in the orders of the Newton coupling. So we decided that we want to follow an expansion scheme which includes all operators that contribute to G Newton to the power of n in the Yukawa coupling. And if we do that, and if we would strictly cut away orders of Gn plus 1, then this would be actually exactly equivalent to a standard perturbative loop expansion to order n. So if we include G squared, then we are doing an exact two-loop computation. Of course, these are not fully disentangled, these expansion schemes. So just because we include operators up to G squared doesn't mean we include operators of all mass dimensions, but instead looking at next to leading orders, so order G squared or order 2 loop, we are at most including operators of mass dimension 8. So yeah, in summary, we are following here option 2, an expansion in the Newton coupling, where we include all operators up to G squared, but we do not cut out contributions at G cubed, but we include all higher resummations that are generated by these operators that contribute to G squared. Okay, so having defined the expansion scheme, let me actually show you what we actually computed. So how do you find these operators that contribute to G squared? And for me, the most intuitive way to identify these operators is actually to look at the beta function, the diagrammatic representation of the Yukawa beta function. And you look at each and every single vertex in this diagrammatic expansion, and then you resum all the vertices that directly contribute to the Yukawa beta function. These are all contributions that start at G squared. So these first 5 diagrams, these are identical to the leading order expansion I've shown you before, but now we include these running vertices that I show here below, and those give you now G squared contributions in these diagrams additionally. These diagrams on the right-hand side, they would be 0. The vertices would be vanishing identically at leading order, but now at next to leading order, these vertices are generated, and also those diagrams with these resummed vertices contribute at order G squared. I'm throwing in here some words induced and non-induced. Please ignore that for the moment. I'm coming back to that in a second. so the thing that I want to highlight here actually is this is a very extensive truncation with many, many different running beta functions. So it's a very extensive set of coupled flow equation that includes an incredibly large number of diagrams that need to be computed. And so at this point, I definitely want to acknowledge and highlight the contributions of my collaborators, Mark and Gustavo. I think what we achieved in computing this incredibly set of beta functions is very it's remarkable. Yeah. And obviously, all of this is only possible if with a good set of codes. And here I want to also use the opportunity to make some advertisement for our new asymptotically safe code base. So if you follow this link, you see all codes that are used in asymptotically safe gravity. And for example, the fluctuation codes of Gustavo, Mark, and me, they're all linked here. And so yeah, automatization to compute this extensive set of beta functions is definitely necessary. All right. I've already thrown in the words induced and non-induced. Let me clarify what I mean with those. So induced operators are actually rather, in some sense, rather straightforward. They take finite fixed point values. And the key point here is that these operators share the symmetry with the respective kinetic terms. So for example, if you have a scale operator, it must have the shift symmetry of the scalar field. At vanishing Newton coupling, they have a Gaussian fixed point, but since they share the symmetry with the kinetic term, they don't have a Gaussian fixed point anymore for finite G Newton. Instead, for small G Newton, they have what is called a shifted Gaussian fixed point. And then for larger G Newton, this shifted Gaussian fixed point can still be there, or maybe it actually can disappear, and the existence is not guaranteed. And testing the existence of this interacting UV fixed point at G Newton is actually a non-trivial test for asymptotically safe gravity. And this goes a little bit under the name of a weak gravity bound, and goes back to Astrid and Holger. And in the recent past, there's been a lot of work in studying these shifted Gaussian fixed point and possible weak gravity bounds associated with that. Here, we are just using these induced operators that have a shifted Gaussian fixed point, and we look what contributions they give to the running of the beta function of the Yukawa coupling. So we are kind of thinking of an induced coupling B. It has some mass dimension, and this receives now a linear contribution from G Newton, from the Newton coupling, and it's linear in G Newton, and it's not linear in B because it is an induced operator. So here, there's no Gaussian fixed point. The beta function, the relevant part of the beta function looks like this, and the fixed point is now given by G star, this coefficient C1 divided by the mass dimension of the operator. Of course, then there's higher order terms, which I'm neglecting here. This operator now we have selected such that it contributes to the beta function of the Yukawa coupling, and consequently, it also contributes to the critical exponent of the Yukawa coupling. So if I look at the critical exponent, the shape that I'm seeing here is that C2 is now the coefficient with which this operator enters to the Yukawa coupling. And in summary, you have G squared. So this is a next to leading order contribution, and comes with these coefficients C1 and C2, and suppressed by the mass dimension. So higher mass dimension still means larger suppression, because the higher the mass dimension, the bigger the suppression here. So this is the first type of operator that we're looking at. The next one is actually a novel one that had been overlooked in the literature so far. Namely, those are non-induced operators. So operators that are asymptotically free, that have a Gaussian fixed point, that are not induced by gravity. Why is that the case? Well, now these operators do not share the symmetry with the kinetic term. So for example, they do not share the shift symmetry of the scalars. So setting them to 0 actually enhances the symmetry of the theory. So they have a guaranteed Gaussian fixed point. Maybe they have a viable non-Gaussian fixed point, but that is, of course, not guaranteed. So the Yukawa coupling is actually an example of that. So the Yukawa coupling has a guaranteed Gaussian fixed point. Maybe it has a non-Gaussian fixed point. Maybe not. And so these type of operators, you would have naively thought, well, they cannot contribute to the critical exponent because the value of the fixed point value is zero. They're asymptotically free. How can they contribute to the critical exponent? But it turns out they can. If, and this is what we need, the non-induced coupling, which I call kappa here, contributes linearly to the Yukawa coupling, and the Yukawa coupling contributes linearly to the non-induced coupling. Then the stability matrix in this simple case has the following shape. It has off-diagonal values. I can now compute this critical exponent in an expansion in G Newton. And what I find is that the additional contribution to the Yukawa critical exponent, which is basically this coefficient here in the top left, it receives this additional contribution, which is of the form G squared, A12 off diagonal term 1, A21, the other off diagonal term, divided by the mass dimension of the operator. So in summary, this contribution is actually exactly the same shape as this one here. G squared, two coefficients divided by the mass dimension, G squared, two coefficients divided by the mass dimension. So it's exactly the same shape. But of course, the origin is quite different. Namely, one has a Gaussian fixed point, while the other coupling has a non-Gaussian fixed point. And this is why it's easily overlooked that these ones can actually contribute to the critical exponent of the Yukawa coupling. All right, so these are the two different types of operators that I will be talking about. And here, I'm showing you the list of all operators that contribute to next to leading order. Left, induced, they share the symmetry with the kinetic term. So typically those are like a kinetic term times some curvature, or just kinetic term squared. While on the right-hand side, these do not share the symmetry of the kinetic term. And as it turns out, all of these are Yukawa-like. So you have Yukawa coupling times curvature, Yukawa coupling times curvature, Yukawa coupling times kinetic term. Actually, if you would have Yukawa coupling times phi squared, so not kinetic term, this would not contribute because it's basically a double zero where you have two parts which do not share the symmetry of the kinetic term. So you can have at most one. Yeah, so these are actually all operators that contribute at next to leading order. Let me mention that we're actually neglecting those in the bottom left. So these are the operators that contribute only to the meta-anomalous dimension. So the anomalous dimension of the scalar and the anomalous dimension of the fermion. And anomalous dimensions typically remain small. And we checked that in previous computations, these contributions indeed were small and negligible. So what we are computing in our work is these two tables sets of operators. I want to make some remarks about these lists of operators, also to convince you that these are actually all operators that there are. So first of all, you didn't see R squared and C squared contributions in the previous table, but they are actually next to leading order, since they contribute directly to the graviton propagator. And although I didn't list them in the previous table, we do take them into account through the momentum dependence of the anomalous dimension. The important thing is we take them into account such that we do not get new propagator poles. And this is guaranteed in our treatment. On the other hand, R squared and C squared contribution to the vertices. So for example, R squared contribution to the free graviton vertex. The free graviton vertex does not directly enter the beta function of the Yukawa coupling. And since there's no direct contribution to the beta function of Yukawa coupling, these contributions are next to leading order. And that's why we are allowed to neglect those without losing our true loop, without losing NLO exact results. there were two operators that were like Yukawa times curvature squared. There's a third one, namely Yukawa times Gauss-Bonnet density. And this is not a topological term. So by itself, the Gauss-Bonnet density would be topological, but since you're multiplying it with the Yukawa term, this is not topological. Nonetheless, it does not contribute to next to leading order. And the reason is that the contribution comes only through a tadpole diagram. And in this tadpole diagram, you have graviton momentum 1 equals minus graviton momentum 2. And in this limit, you fall actually back to the topological term, and the vertex is actually vanishing exactly. So this is not next to leading order. This operator here, Yukawa times kinetic scalar term, I've listed before, and it is a next to leading order operator, but actually it vanishes in our computation. So, and this is due to a gauge choice. So we work in alpha 0 and beta 1, and just for this particular gauge choice, this operator is vanishing. This is actually very similar to what we've observed previously, namely that the scalar anomalous dimension is also vanishing for this particular choice of gauge fixing parameter. So this is an NL operator, but just coincidentally vanishes. There's actually a lot more operators, so I'm just choosing some remarks on some special ones. So here, for example, I'm choosing the Yukawa times kinetic term of the fermion. And the only thing that I'm doing is I'm moving the gamma matrix from the kinetic operator to the Yukawa term. And now this operator, I've barely changed it, but now it does not contribute anymore due to its Dirac structure. So basically, when you take the Dirac trace, this operator vanishes. So to summarize, there's a lot of operators, but a lot of them vanish either through considerations of momentum dependence or Dirac structure, or in this one edge case also due to gauge fixing choices. And after all these considerations are taken into account, this is the set of operators that we are left with. All right. Then just a few quick remarks on how we compute the beta functions. We use finite momentum projections for induced couplings and also for the anomalous dimensions. So I already mentioned the anomalous dimensions. We want to capture, for example, the R squared and C squared contributions. And so we want to keep their momentum dependence. At the same time, we are doing a derivative expansion of the Yukawa-like coupling. So all couplings that are asymptotically free that enter in the stability matrix, of those we do a derivative expansion. And those terms, those operators contain up to 4 derivatives. So we need to do a derivative expansion up to 4th order. And because of that, we actually need to use a higher order lithium regulator. So what we're using here is this regulator function below. For n equals 1, you would have the standard lithium type regulator, but we are using it with n equals 2. This is the bosonic regulator, and we choose the fermionic regulator analogously, such that this relationship here holds that the regularized fermionic dispersion is the square root of the regularized bosonic dispersion. This is just it's a short remark on how we then compute these beta functions. And now let me come to the results. And first of all, main result, if there's anything you should definitely take away from today, is at next to leading order, the Yukawa coupling is relevant at the Gaussian fixed point. So at leading order, we found negative critical exponent. And now at next to leading order, the critical exponents are positive, here for minimal matter and here for standard model matter. Here I'm also already including an error estimate on these critical exponent, and I will explain you in a second how we get to this error estimate. But as you can see, the critical exponents are positive, and even without outside of the and 0 is not compatible with our error estimates. Okay, so this is the main result. Let me walk you a little bit through how we get to this and dive a little bit deeper into these results. So first of all, we actually need to find an interacting UV fixed point. As I mentioned before, this is possibly one of the largest truncations in which a gravity matter system in asymptotic safety was studied. So it's actually already non-trivial that we find an interacting UV fixed point. So we have the Newton coupling, the cosmological constant, plus all these induced operators. And all of these operators need to have an asymptotically safe fixed point. And indeed, we find all of them have an asymptotically safe fixed point, but also we find that the only relevant directions are associated with the Newton coupling and the cosmological constant. So we have two relevant directions in these induced couplings, and all of the other ones are irrelevant. And most of them are rather close to their canonical mass dimension. So the canonical value of the critical exponent would be -2, and most of them are aligned, have a critical exponent around -2. Then separately from that, we have the free fixed point in Yukawa sector. So all Yukawa-like couplings are vanishing. They are non-induced. By definition, they have a free fixed point. And at this free fixed point, we can again compute the critical exponent. And what we see is the critical exponent associated with the Yukawa coupling is large and positive. This is the biggest deviation from the canonical expectation, while all the other ones have critical exponents which are irrelevant and rather close to their canonical expected value. Let me also mention that all the fixed point anomalous dimensions are well behaved, so all of them are rather small, and all of them are particularly smaller than 2, where we would lose control of our truncation. This is for minimal matter, and just to say, for standard model matter, we also find that we have an interacting UV fixed point, 2 relevant directions in the Newton coupling, even closer alignment with the canonical critical exponents in these induced couplings. So all of them are basically very close to -2. Again, we have a free Yukawa sector. We have a relevant Yukawa coupling, and then we have irrelevant Yukawa-like couplings. And again, we have very well behaved fixed point anomalous dimension in the sense they are all rather small. So these are already non-trivial results, existence of a fixed point, and then on top of that, we find that in the system, the Yukawa coupling is relevant. Now I've written down a very large truncation, and of course, we would like to better understand which operators are actually now responsible for the fact that the Yukawa coupling becomes relevant. And for this, it's actually very good to make a strict loop expansion, so to throw away all terms above g squared and only retain those contributions which are up to order g squared. So here the first line is for minimal matter, so the leading order coefficient is negative, as is already discussed, and then the sum of all two-loop coefficients is positive. And now splitting them up, we see that there's positive, negative contributions from different operators. We also see that the non-induced operators, so the Yukawa-like couplings, give far more stronger contributions than the induced ones. So back here, are all the induced ones. These are all small numbers compared to, for example, the R-squared Yukawa coupling, which is the dominant contribution for minimal matter. For standard model matter, the picture is very similar. Leading order term negative, two-loop term positive. Again, the Yukawa-like couplings have a far larger contribution than all the induced couplings. The most dominant one in case of the standard model is the fermion Yukawa, closely followed by the R-squared Yukawa. Here is actually so here the difference between minimal matter and standard model matter is, simply speaking, the multiplicity of fermions. Here we have 1 fermion, and here we have 22.5 fermions. So evidently, this gives a larger contribution in the standard model case. So the two-loop coefficient is positive. And actually, another thing I want to remark is that meta fields actually make the Yukawa coupling more relevant. So if you look at this, so the scalar Yukawa, so the only place where you have explicit and F and S and vector multiplicities are in the fermion Yukawa, gauge Yukawa, and the scalar Yukawa. The scalar Yukawa is not here because, as I mentioned before, it's vanishing. But the coefficient of the fermion Yukawa and the gauge Yukawa is both positive. So adding more matter fields should actually help to make should not destabilize this result that Yukawa coupling is relevant. All right. So next, I want to show you how stable our result is with changes to the fixed point values. So this is very analogous to the plot that I've shown you in the beginning. So dependence on the Newton coupling and the cosmological constant, left minimal matter, right standard model matter, and red region means here the Yukawa coupling is irrelevant. No vanishing Yukawa couplings in infrared. In the green means Yukawa is relevant and we can generate finite Yukawa couplings. We have the separation line as well as an error from the next to leading order operators, which I will explain in a second how we estimated that. We have a gray line here, which indicates where anomalous dimensions become large. This is also shown here in the inset plot. So in this region, we would not trust our truncation anymore necessarily. In both cases, you see that the fixed point value is located, inside the green region, very well inside the gray region, away from the region where the anomalous dimension becomes large, away from the region which is our error estimate. Maybe just to emphasize, I did not forget the error estimate here on the right-hand side. The error estimate here is actually very small, and I will also come to the that why this is actually such a small error region here. All right.
Manuel, you're about 45 minutes in, so if you could wrap up in the next 5 to 10 minutes, that would be good.
Yeah, should be fine. All right. So let's talk about the error analysis. This is also the last major point that I want to make. So let's think how a possible next to leading operator would contribute. And what you should roughly think about here is R cubed times Yukawa. Like this was at R squared. Yukawa was a very dominant operator. So think of this as a typical next leading order operator. That makes total sense. Why is it next to leading order? Is actually because it does not have a direct contribution to the beta function of the Yukawa coupling. It also doesn't have a direct contribution to the box Yukawa, but this is really the main part here. And because of this property, you have here two zeros in the stability matrix, which basically makes it a higher order operator. It also has mass dimension 10. So the diagonal element here is a 6 now, because for space-time dimensions, etc. And now if I look at this operator and I would do an expansion of the Yukawa critical exponent, I would find that the contribution comes with g cubed as expected, combination of this divided by 6. So this is the suppression factor that we are expecting from a next to leading order operator. So now, how can we don't want to compute this operator. This is obviously a hard task. So instead, we want to estimate what uncertainty this operator introduces to our Yukawa coupling. So for this, we need to find an estimate how large these numbers might be, and this would allow us to simulate the uncertainty of our result. So for this, we actually looked at the next leading order matrix and thought, well, the naive thing one can do is one looks what is the range of coefficients that you find here. That's the range in which you simulate and which you guess the numbers of the next leading order operators, and that's it. But this is actually not the best thing to do because there's a lot of freedom in the next NLO matrix. It's not scheme independent. So if I redefine my coupling, I'm not changing the critical exponent, but I'm changing the coefficients in the stability matrix. So if I look here, this is now the original stability matrix. And here we have coefficients which are of order 1,000, but also very small coefficients. And I'm selecting these two because typically the coefficients which are opposite to each other are entering in a combined way in the Yukawa cup, in the critical exponent. So this is multiplied with this one. So actually one can use the freedom to rescale couplings and choose a different coupling basis to homogenize this matrix. So this matrix that I'm showing you below, M tilde, has exactly the same critical exponents. And now this number here is smaller and balanced by a number which is of the same order of magnitude. So now in this balanced, homogenized NLO matrix, we have a much better guess of what these numbers in the next to leading order might be. Namely, we are just looking at this NLO matrix. We are selecting the largest entry of this homogenized matrix. And now we are generating random entries for these coefficients in the stability matrix, precisely in this range that was defined by the next to leading order matrix. We do this a couple of times, 10 to the 5 times, and compute each time the critical exponent of the Yukawa coupling. And this defines now, with this we use to define the error of theta y under the influence of one next to leading order operator. And if you do that, now I'm showing you the error bars more explicitly as a function of the Newton coupling. I'm also showing you the critical exponent of the Yukawa coupling as well as the higher dimensional Yukawa-like couplings. And at small g Newton, obviously, the error bar is very small, and then it increases as we increase g Newton. And here is the fixed point value of g Newton. And of course, at g star, we have rather large error on the Yukawa coupling, which you can see on the right. And here, these are large errors. But both of the error bars are not compatible with 0. And also, there's a very small uncertainty on this transition range from negative Yukawa coupling to positive Yukawa coupling. And this is precisely the reason why, in this plot that I've shown you before, this error bar is rather small. We have a large error on the critical exponent, but we have a small error on the transition period. All right. And yeah, with this, let me actually summarize what I've told you today. So I hope I convinced you that it's very important to understand what is the interplay of gravity and Yukawa interactions. And if we want to have fundamental Yukawa interactions in asymptotically safe gravity, we need that this critical exponent is positive. And we computed this critical exponent to next to leading order. We did this by resumming higher order operators, induced and non-induced. And as it turns out, the non-induced ones are the dominating ones. And yeah, so we have achieved this by rather extensive truncation in the matter sector. And actually, we found that in this extensive truncation, there is a near perturbative UV fixed point for minimal matter and standard model matter. And that the critical exponent of the Yukawa coupling is relevant at the Gaussian fixed point. So here, again, the values that we are finding together with the error bars that I've explained now in the last slide. So we have large error bars on the value, but they're not compatible with 0. So we are very confident that actually we have a relevant Yukawa coupling at the Gaussian fixed point. Along with that, we have actually developed a new conceptual way of estimating these errors, namely from the missing contributions of next to leading order operators, simulating potential entries of these next to leading order operators. And we've developed a new understanding in terms of these metacritical exponents, namely that non-induced operators can contribute via these off-diagonal entries in the stability matrix. So they can contribute, although they're asymptotically free, although their fixed point values are 0. And yeah, we definitely want to use that to also provide in the future re-evaluations of the critical exponent of the gauge coupling and of the critical exponent of the quartic scalar coupling. And with that, I want to thank you for your attention.
Yeah, thanks a lot, Manuel, for the talk.